Hello, everyone, and welcome to our discussion on OSST, or Alternative Waste Systems. Today's lesson is part of our continuing series on engineering utilities. In our previous lecture, we focused on the design of pipe networks for sanitary systems. Now, we will shift our attention to understanding wastewater, its classification, and the different sources from which it comes. This topic will help us build a solid foundation for future lessons on plumbing system design. Let us begin by defining what wastewater actually is. Wastewater, which is also known as sewage, refers to used water. It contains waste products, excrement, and other discharges from the bodies of human beings or animals. In some cases, it can also include harmful or poisonous substances that are dangerous to public health, harmful to animals or aquatic life, and even affect how water can be used for drinking, bathing, or recreation. In short, wastewater is any water that has been contaminated after being used, and it needs to be treated before being released back into the environment. Wastewater can be divided into two main categories. The first category is called black water, and the second is called gray water. Black water is wastewater that contains fecal matter and urine. This type of wastewater is produced in water closets or toilets, urinals, and bidets. On the other hand, gray water is wastewater that usually contains residues from washing processes. This includes water coming from bathtubs, showers, sinks, lavatories, and clothes washing machines. Understanding these two categories is very important because they are treated differently in plumbing. Let us look at a few examples. Some simple examples of black water include fecal matter and urine. These are the primary waste materials that make black water more hazardous compared to gray water. Gray water, on the other hand, comes from washing activities. For instance, when we take a bath, wash our hands in the sink, or do our laundry, the water that flows out afterward is considered gray water. Having seen examples, let us review their sources. The sources of black water are water closets or toilets, urinals, and bidets, while the sources of gray water are bathtubs, showers, sinks, lavatories, and clothes washing machines. Being able to identify where each type of wastewater comes from will be helpful when we discuss treatment and disposal methods later. Black water can actually be separated even further into two more specific types, which are yellow water and brown water. Brown water is wastewater that consists mainly of fecal matter mixed with flush water. Depending on the separation system used, it may or may not include urine. Brown water is common in systems where solids are collected separately so that they can be treated or composted. Meanwhile, yellow water consists only of urine without any fecal matter or flush water. Yellow water is collected separately in some ecological sanitation systems to recover nutrients, which can be used as fertilizer after proper treatment. To make it clearer, yellow water is basically urine combined with flush water or wash water. Brown water, on the other hand, is fecal matter mixed with flush water or wash water. Being familiar with these terms will make it easier for us to understand modern waste separation and recycling systems. Now that we have classified wastewater, let us define OSST, also known as on-site sewage treatment. This is what we often call a septic system. It usually begins with the building sewer that carries wastewater from the house. From there, it enters the septic tank, then passes to a distribution box, and finally flows into an absorption field, also called a drain field or disposal field. Each of these parts plays a role in treating and dispersing wastewater safely. Let us focus first on the septic tank itself. A septic tank is a vault or receptacle that collects organic waste from the house sewer. Its main function is to liquefy and precipitate solid waste while purifying materials that would otherwise create odor. Inside the tank, three main layers or types of byproducts can be observed. First is the scum layer. This is made of substances lighter than water, such as oils, grease, and fats. They float to the surface, where aerobic bacteria help break them down. Second is the sludge layer. These are the heavier solids that settle at the bottom. In this layer, bacteria that thrive without oxygen break down biodegradable matter. Third is the effluent. This is the liquid portion that eventually exits the tank into the drain field. Effluent may be treated or untreated wastewater, depending on the system. Overall, The septic tank holds wastewater long enough for solids to settle and for oils and grease to rise. This separation allows the liquid effluent to flow onward. A well-designed tank usually provides around 2 days of retention time for this settling process to occur. Septic tanks can be built using many different materials. In this discussion, we will look at some of the most common types, but keep in mind that there are many other variations as well. Concrete septic tanks, whether precast or cast in place, are among the most widely used. They are durable, capable of carrying heavy loads such as vehicles passing overhead, and, when properly sealed, can resist corrosion from surrounding soil. Cast-in-place tanks are often preferred for projects where site-specific customization is needed or where transporting a precast tank would be impractical. The main drawbacks are their weight, which requires heavy equipment for installation, and the potential for cracks to develop over time if the soil settles. They also tend to cost more compared to plastic or fiberglass options. Masonry septic tanks are built on site using concrete hollow blocks or bricks plastered with mortar. Their main appeal is flexibility. They can be customized in size and shape to fit almost any site, and the materials are often affordable. Repairs are also fairly straightforward. Still, this type of tank relies heavily on workmanship. Poor plastering can cause leaks, and overall, their service life is shorter than that of solid concrete tanks. Plastic septic tanks, typically made of polyethylene or high-density plastic, are factory molded and lightweight. Because of this, they are easy to transport, install, and resistant to corrosion. But lightweight construction also brings challenges. In areas with a high groundwater table, these tanks can float if not anchored. They may also deform under soil pressure if the backfill is not done carefully, and their capacity is limited for larger households. Fiberglass septic tanks look similar to plastic tanks, but are stiffer and stronger thanks to fiberglass reinforcement. They are leak-proof, lightweight, and easy to handle without heavy machinery. On the downside, they cost more than plastic tanks and can still float if groundwater levels are high. They also require careful handling during transport and installation since the shell can crack on impact. FRP, or fiber-reinforced plastic septic tanks, are designed with industrial-level performance in mind. They combine high strength with lightweight and are extremely resistant to chemical attack, making them suitable for specialized or industrial waste. However, they are also among the most expensive, require careful installation, and in many residential cases, they may be more than what is actually needed. Stainless steel septic tanks are uncommon for homes but worth mentioning. They are strong, resist corrosion better than ordinary steel, and can last a long time if properly maintained. The trade-offs are their high price, susceptibility to pitting corrosion in aggressive soils or coastal areas, and the fact that they are rarely available for residential projects. With so many options, it is important to consider several key aspects when choosing what material to use for a septic tank. Let us go through them one by one. The first factor is durability and lifespan. Concrete tanks may last for decades, while plastic tanks may degrade faster if exposed to sunlight when not buried. Resistance to cracking, corrosion, and impact should always be evaluated. Next is structural strength. A septic tank must withstand soil pressure and sometimes even vehicle loads if installed under driveways. Concrete is superior in load-bearing capacity compared to most other materials. Installation is another important consideration. Concrete tanks are very heavy and require equipment for delivery and placement, while plastic and fiberglass tanks are lightweight and easier to handle by hand. Site accessibility is also a factor, especially for remote locations where heavy machinery cannot reach. Cost and budget must also be weighed. Masonry tanks may be cheaper but require more labor. Stainless steel and FRP tanks are very durable but come with high prices. Always include transport and installation in the total cost. Maintenance is also part of the decision. Concrete and masonry tanks can be patched or repaired when cracks appear. Plastic and fiberglass tanks, however, are more difficult to repair and may need full replacement if damaged. Access for inspection and cleaning should also be considered. Local regulations and availability can influence the choice. Some areas have building codes or health department rules that only allow certain tank types. It is also practical to use materials that are readily available in the region to avoid delays. Site conditions also play a big role. Heavy concrete tanks require soil with good bearing capacity. In areas with a high water table, plastic or fiberglass tanks may float unless anchored. If the soil is corrosive, materials like plastic fiberglass or FRP perform better than concrete or steel. Finally, capacity and intended usage matter. A large household may require a reinforced concrete or masonry tank to handle the volume. For industrial or chemically aggressive wastewater, FRP or stainless steel may be more suitable. Matching the tank to both household size and waste type ensures long-term performance. According to Appendix B, the required capacity of a septic tank depends on either the number of bedrooms or apartment units, or the estimated design flow rate of wastewater. For other types of buildings, the basis can be the number of plumbing fixture units, whichever value is greater. Tables B-2 and B-3 provide these references. In addition, the maximum size of a single septic tank and its drainage system is limited by the soil classification, which is given in Table B-5. This ensures that the tank is not only large enough to handle the load, but also compatible with the soil where it will be built. When it comes to concrete and masonry septic tanks, the preferred shape is rectangular. There are several important reasons for this preference, and I will go through them one by one. First, rectangular tanks are easier to construct. Concrete tanks can be cast in place or made with precast panels, while masonry tanks are built using hollow blocks or bricks. Straight walls are simpler to form and lay out compared to curved surfaces, making construction faster and more reliable. Second, rectangular tanks make better use of space. They can fit neatly into narrow or irregularly shaped lots, and the layout makes it straightforward to separate the different chambers, such as the inlet chamber, settling chamber, and outlet chamber. Third, the shape gives structural simplicity. Reinforcing straight walls with steel bars is much easier, and applying plaster evenly ensures proper water tightness. Even the top cover benefits from this design, since flat slabs are simpler and more economical to cast than circular covers. Fourth, rectangular tanks are cost-effective. They do not need specialized curved formwork, which reduces material and labor costs. Since masons work faster on straight walls, the overall construction becomes more affordable. And fifth, maintenance is more manageable. Rectangular walls and corners make it easier to install baffles and access manholes. During cleaning or desludging, the predictable chamber layout also helps workers perform the task efficiently. With all that said, next concern will be how to design a septic tank. In B5.4, the requirements for septic tank compartments are shown. Every tank must have at least 2 compartments. The inlet compartment, also known as the digestion chamber, must hold not less than 2/3 of the total liquid capacity. It must also be at least 2 cubic meters in volume, not less than 0.9 meters wide, and 1.5 meters long. The liquid depth should be no shallower than 0.6 meters and no deeper than 1.8 meters. The secondary compartment, also known as the leaching chamber, should have a volume of at least 1 cubic meter, and not more than 1/3 of the total tank capacity. For tanks larger than 6 cubic meters, the length of the secondary compartment must be at least 1.5 meters. To make calculations easier, we can use standard abbreviations. IC refers to the inlet compartment or digestion chamber. OC refers to the outlet compartment or leaching chamber. And VLC refers to the volume of liquid capacity. So let's go over each of the statements. Septic tanks must have a minimum of 2 compartments. This can be achieved by placing a wall in the middle. Imagine a simple tank divided into 2 white spaces. Let me emphasize that in the figures shown, the white portion represents the inside of the tank. However, let me emphasize that in some cases, local ordinances require more than 2 compartments, where in some localities 3 is the minimum. This means that before designing or building, we must always verify the local requirements to ensure compliance. For our discussion, we will concentrate on the 2-compartment system, since this is what the code specifies as the standard. Moving on to the next statement. The inlet compartment must follow specific rules. Its length should not be less than 1.5 meters. Its volume should be at least 2/3 of the total liquid capacity of the tank. It must also not go below 2 cubic meters. And the minimum width is 0.9 meters. These measurements ensure that the inlet chamber functions effectively as the primary digestion zone. Next, let us look at liquid depth. The liquid depth of the tank should never be less than 0.6 meters and should not exceed 1.8 meters. This range ensures proper settling of solids and prevents operational problems. Now, for the secondary compartment, its volume must not be less than 1 cubic meter. At the same time, it cannot exceed 1/3 of the total liquid capacity of the tank. This balance makes sure that the outlet side functions well in clarifying the wastewater. When the total capacity of a septic tank exceeds 6 cubic meters, an additional rule applies. In that case, the outlet compartment must have a length of at least 1.5 meters. This requirement ensures that larger tanks maintain effective separation between compartments. Another important part of the code deals with access. Each septic tank must have at least 2 manholes. Each manhole should have a minimum dimension of 0.508 meters, or there must be an equivalent removable cover slab. One manhole must be placed at the inlet side and another at the outlet side. Furthermore, if the first compartment is longer than 3.7 meters, then an additional manhole should be installed above the baffle wall. In the first statement, it says that every septic tank must have at least 2 manholes. The clear opening of each manhole should measure no less than 0.508 meters. This requirement ensures proper access for maintenance and inspection. The next statement highlights placement. One manhole should be located directly above the inlet side, and the other directly above the outlet side. These locations make it easier to inspect flow and handle any needed cleaning or repairs. And finally, if the first compartment of a septic tank is longer than 3.7 meters, another manhole is required above the baffle wall. This extra opening provides access to the middle portion of the tank, which is critical for desludging and long-term maintenance. Here we can see the location of the inlet and outlet baffle fixtures. These are the key points where wastewater enters and leaves the septic tank, and the baffles control the flow between compartments. Let us now look at the code under section B5.6. This provision sets the requirements for the inlet and outlet pipe openings, as well as the fittings and dimensions that must be followed. The first statement tells us that the inlet and outlet pipe openings should never be smaller than the connecting sewer pipe. In other words, the baffles must match the size of the connecting pipe. For round fittings, the vertical leg must not be smaller than that same connecting pipe, and in no case should it be less than 104.6 millimeters. This ensures smooth flow and avoids clogging. Next, if we are using a baffle-type fitting, its cross-sectional area must be equivalent to that of the connecting sewer pipe. In addition, its horizontal dimension at the level of the inlet and outlet pipe inverts must not be less than 106.6 millimeters. Now, the term pipe invert simply refers to the lowest inside surface of the pipe, or the base where the wastewater flows. So at that level, we must respect this minimum horizontal size. Section B5.7 deals with how far the baffles should extend above and below the water surface. The rule states that the inlet and outlet pipe, or baffle, must extend 101.6 millimeters above and at least 304.8 millimeters below the water surface. The code also specifies that the invert of the inlet pipe must be at least 50.8 millimeters higher than the invert of the outlet pipe. This means that both the inlet and outlet baffles extend vertically, 101.6 millimeters above the waterline, and 304.8 millimeters below it. This arrangement helps guide flow and maintain proper separation of scum and sludge. At the same time, the inlet pipe is slightly higher than the outlet pipe. Specifically, the inlet invert must sit at least 50.8 millimeters above the outlet invert. This small drop ensures wastewater flows smoothly through the tank without backing up. Moving on to section B 5.9. The code requires that the side walls of the septic tank extend at least 228.6 millimeters above the liquid depth. This extra height prevents overflow and provides freeboard inside the tank. The same section also specifies that the cover of the septic tank should be at least 50.8 millimeters above the back vent openings. This arrangement ensures proper venting while keeping the tank sealed and safe. To prevent corrosion, it is also very important to waterproof the constructed concrete or masonry water tank. In section B5.13, it mentioned tanks must be waterproofed specifically using bituminous material. Another important design detail is the slope of the bottom of the digestion chamber. The floor should be sloped toward a low point. The purpose of this slope is to collect the settled organic matter in one place, which helps anaerobic bacteria grow and break down the waste more effectively. There are several methods for determining the size of a septic vault. In this discussion, we will follow the recommendation of the National Plumbing Code of the Philippines, as outlined in Appendix B. The process goes like this. First, identify the total drainage fixture units of the structure using Table 7-2. Next, use that value to find the required liquid capacity from Table B-2. Then, assume reasonable values for the width and the height of the tank. After that, compute the chamber lengths based on the provisions in Appendix B. And finally, refine the dimensions to account for constructability and the actual site conditions. By following these steps, we ensure that the septic tank design is both compliant with the code and practical to build. Let us go through an example to apply the process. Suppose we have a residential building with 1 kitchen and 6 bathrooms. Each bathroom contains 1 lavatory, 1 water closet with a bidet, 1 shower and 2 floor drains. Since the requirement is only for black water, we will focus on the water closets and the bidets. With 6 bathrooms, that gives us 6 water closets and 6 bidets. Now, let us check the National Plumbing Code of the Philippines, specifically Table 7-2. In this table, the bidet is listed in row 2 with a value of 2 fixture units, while the water closet appears in row 29 with a value of 4 fixture units. Multiplying these values, 6 bidets correspond to 12 fixture units and 6 water closets correspond to 24 fixture units. Adding them together, the total drainage fixture unit for black water comes out to 36. Let us open Table B-2. So as you can see, 36 fixture units is between 33 and 45. With that said, we must apply interpolation to solve for the minimum capacity, corresponding to the calculated fixture unit value of 36. Let me show you how we can streamline this calculation using a generic PRC accredited calculator. While each model may have slightly different button layouts, their functions are generally the same. For this example, we'll switch to stat mode and use it to perform the interpolation. Then choose option 3 to activate stat. Next, press 2 to select linear equation. In the table, enter 33 and 45 under column X. Then, enter 5,677.5 and 7,570 under column Y. These are the values of the capacity in liters. Finally, clear the display by pressing AC while keeping the data stored in memory. We then press Shift 1 to open the stat functions. Then select option 5 for regression functions. Next, choose Y current. We place the insertion point of the calculator before Y current by pressing the left arrow key, and then we enter 36, which is the target fixture units. Press equals, and the calculator gives us the corresponding capacity for 36 fixture units. The computed capacity is 6,150.625 liters, and this will serve as the minimum required capacity. This value also represents the total liquid capacity of the septic tank, written as V sub LC. To convert it into cubic meters, we divide the liters by 1,000. According to section B 5.4, the minimum septic tank width is 0.9 meters. For this example, let us assume a width W of 1.5 meters. The same section specifies that the liquid depth must be between 0.6 meters and 1.8 meters. For simplicity, we will assume a liquid depth of 1.2 meters. We also know that the inlet compartment must hold at least 2/3 of the total volume, or a minimum of 2 cubic meters. Meanwhile, the outlet compartment is limited to 1/3 of the total volume. If we compute the volume of the inlet liquid capacity, we obtain 4.101 cubic meters. And the volume of the outlet liquid capacity is 2.050 cubic meters. As per code, the inlet compartment volume must be greater than 2 cubic meters. Our computed value of 4.101 is acceptable. If the computed volume were less than 2 cubic meters, we would replace it with the minimum value of 2 cubic meters. The outlet compartment must also have a volume greater than 1 cubic meter. The computed value satisfies this requirement as well. And so, to solve for the compartment length, we divide the volume by the assumed depth and width. The inlet length is computed to be 2.278 meters, which when rounded up becomes 2.3 meters. This must then be compared to the code requirement of 1.5 meters. If the value is smaller than 1.5, we adopt 1.5 meters. The outlet compartment length is 1.139 meters, which we can conveniently take as 1.2 meters. Although rounding down the outer compartment length would technically keep the volume under 1/3 of the total, the difference is minimal and will be compensated for by the rounding up of the interior compartment length. For the sake of uniformity, since the interior compartment was rounded up, it is more consistent to round up the outer compartment as well. However, as per code, if the total liquid volume is greater than 6 cubic meters, the outlet compartment length must be at least 1.5 meters. In our case, the total volume indeed exceeds 6 cubic meters. This means the outlet compartment length of 1.2 meters is insufficient, so we replace it with 1.5 meters. Finally, the total length is the sum of the inlet and outlet lengths. The total tank length is therefore 3.8 meters. Now, based on the code, the minimum wall extension is 228.6 millimeters. Let us assign d extension as the extension variable. So d extension is 0.229 meters, or when rounded up, it becomes 0.3 meters. The total depth is then equal to the liquid depth plus the extension. So d is 1.2 plus 0.3, which results in 1.5 meters. To summarize the computation, the septic tank dimensions are 1.5 meters by 1.5 meters by 3.8 meters. Finally, if we go beyond the computation requirement and consider the length of the inlet compartment, the value is 2.5 meters. Since this is less than 3.7 meters, no additional manholes are required. The design result of 1.5 by 1.5 by 3.8 meters might seem a bit impractical for actual construction, especially the length. In a real project, we could further refine this by adjusting some of the parameters, especially the width and the liquid depth of the septic tank. For instance, setting the width to 2 meters and the liquid depth to 1.5 meters would help shorten the overall length. For this example, though, we'll keep it as is. We might not be able to cover them in this short lecture, but take note that there are some other parameters that can be found under Appendix B. For example, in Table B-1, we find additional details such as the required location of a sewage disposal system. For septic tanks, the minimum distance must be 1.5 meters away from any building or structure, or from an adjoining property line, and it must be at least 15.2 meters away from water sources, such as wells. Moving forward, there are also requirements that help us determine whether the disposal of human waste is satisfactory. These criteria guide us in making sure that the system is safe and effective. First, there should be no contamination of the ground surface that could seep into springs or wells. Second, there should be no contamination of surface water. Third, the surface soil itself should not be polluted. Fourth, excreta must not be accessible to animals, flies, cockroaches, vermin, or similar carriers of disease. And finally, there should be no unpleasant odors or unsightly conditions around the disposal site. In most cases, septic tanks are poorly aerated or ventilated. They lack free oxygen. Under this condition, a person who enters the tank for repairs or cleaning may face almost instant death. This is because septic tanks may contain harmful and dangerous gases. That is why, before any repair work or cleaning is carried out, the tank must be properly ventilated. One safe practice is to remove the manhole cover a few days in advance of the work. Another precaution is to supply fresh air inside the tank while the work is being done. We must also remember that septic tanks can contain flammable gases, which may ignite and cause a violent explosion. If lighting is needed inside the tank, only an electric emergency lamp with a properly insulated cord should be used. In the absence of an electric source, a flashlight powered by a dry cell battery is a safe alternative. With that said, let us look at an example of the plan view of a septic vault cover. Next, here is a sample plan of a septic vault. And here, we can see a longitudinal section of a typical septic vault. It is important to understand that the plans shown here may vary depending on the specific requirements of the design, as well as additional provisions set by local laws or ordinances. That would be all for now. Thank you guys for watching, and I'll see you on the next one.